Hello students, and welcome to the pre-lab video for thermal expansion. So suppose we have a long thin rod like this of a pure metal. In this case, this one is copper. It has a particular length at room temperature. It turns out if we raise the temperature, the rod will increase its length. And it turns out this change in length, this increase in length, is directly proportional to the increase in temperature. And the constant of proportionality is something we call the coefficient of linear expansion. So this is an important property of many solid materials. And today we're going to experimentally determine the coefficient of linear expansion for a particular pure metal. So you may have copper, you may have iron, you may have brass or aluminum. Now we're going to use the Senko linear expansion apparatus, and I have one right here, and we see there's a housing like this, and inside there is one of these thin rods of a particular metal. Now one thing you will have to do is measure the length of the rod at room temperatures, so you will need that. So you will need to disassemble this, pull this out and measure it and put it back together. There are two rubber stoppers at either end, and the metal rod is inside the two rubber stoppers, and it's centered into the housing there. So a few features of the housing: there is a little screw at this end, and then at this end there is a screw attached to a dial, and this allows you to record the initial length, not really the initial length, but the initial position of the rod on one end. And then we can, when it expands, take another measurement, and between the two we can determine the change in length. And let me show you how we would do that. So you'll see there are two measuring scales on this end of the expansion apparatus. There's one here in millimeters, a linear straight one there, but there's a dial scale that's in 1/100ths of millimeters. And every time I turn this around one time, it will go in or out exactly 1 millimeter. So I'm able to get a measurement down to a change in distance down to a 1/100th of a millimeter. So that's very good, because the change in length will not be, relatively speaking, a lot. It will be probably less than a millimeter. So I would, at room temperature, put my rod in there, and then I want to make contact with the screws at both ends so that I'm sure I'm getting an initial reading here at the initial length of the rod at room temperature. So to be sure that you're correctly doing that, there's an electrical circuit in here, and when I make contact with the dial here and with the screw here, a little light bulb comes on right here. So you'll notice that. That tells you, hey, you're ready to take the measurement down here. So I would go down here to the dial and to the linear scale, and suppose on the linear scale the front face of my dial is between 1 and 2 millimeters, and then the dial, the 1/100th, is maybe at 20. I would record that. Hey, I'm between 1 and 2 millimeters on the linear scale. Dial is at 20 1/100ths of millimeters. I would record that. And then it's very important that we back out several turns here to allow for expansion. Now I want to heat the linear rod up. So you'll see you have a thermometer right here, a little manual thermometer. And we're going to heat it up using a device we call a steam generator. And it's a very simple device, and we simply put water in it. There's a sight glass here that will let you know the level of the water inside. If you use too much water, you'll have to wait too long to get your steam. Too little water, it will evaporate before the experiment is done. Probably fill it about half full, and you can tell that by looking at the sight glass. And then you would simply plug it into a receptacle, and it will generate steam. So I would attach the hose from the steam generator to this end of the tube. So it will take 5 to 15 minutes depending upon your steam generator, and you eventually will see steam coming out the exit point of the cylinder right here. So you want to let it heat for maybe a good 5 or 10 minutes like that, and then you can look at the thermometer right here and get a temperature, a final temperature above room temperature. It will be about 100 degrees C, obviously. Now, another way to get the final temperature is if you know the barometric pressure, you can go to a steam table and get the temperature for steam for that given pressure situation, and sometimes that's a little more accurate. So I don't know what will be available to you. You would need a barometer and a steam table, so perhaps that would be available. Maybe you would just use the thermometer right here. So once we get it fully heated up, we've let the steam flow through it 5 or 10 minutes, and we record our final temperature. We want to get a new reading on the dial down here, so I would tighten it up again. I would bring it in with it at the elevated temperature and until I see the bulb illuminate down there. And at that point, I would go down here again. I would look where the front face of the dial is on the linear scale, and maybe it's a little bit beyond 2 millimeters now, between 2 and 3 millimeters, and my dial is, say, at 10. I would record that, and that would tell me, hey, I had an increase of 90/100ths of a millimeter. And that would give me my delta L, or my linear expansion. And now with the original length and my change in temperature, I have everything I need to determine the coefficient of linear expansion for that material. I can compare it with the known value and compute a percent difference. So very easy setup to use, and if you're very careful and you record the measurements here correctly, you'll get very, very good results, and you should get a low percent error. So I hope you will review this before you come to the lab to study thermal expansion. So I look forward to seeing you in the lab.